And I want to spend a few minutes telling you about this. And it's worth starting off the way Dick Cheney starts off on any problem by saying what it is we actually know. And so first we have the known knowns in this example. And this, for what I'm going to tell you today, would be a representation of the canonical biochemistry. So I'm not going to tell you about problems where we really don't know anything about the potential reaction mechanism, and we have to infer that directly either by human intuition or automated methods, and my lab and others work on that as well, but I'm not going to talk about that. So here's a case where we have a plausible reaction topology. You know many, if not all, of the players, but we have a couple of alternatives we want to distinguish. Absolutely critical, of course, is we don't really know the rate constant of any reaction. And we're going to have to deal with that relative unknown sort of information because rate constants must matter. There's a lot of speculating in this community about robustness, and rate constants don't matter in the amount that doesn't matter. You're supposed to be robust to those features as though there would be no kinetics. So I think that like those small changes in the concentration is critical. So the basic logic, many of you may be familiar with, is we do still start with a hand-annotated diagram of some sort. And so let me just imagine now, half phase 8, that very first step, the one that we were in fact imaging in those living cells, coming along, reacting with VID, and creating reactive clean cells. And of course what we do is we can break that down into sort of elementary binding and catalytic reactions. And then what we do is we simply write that out as a differential equation. The differential equation looks relatively unfamiliar to you, but it is precisely, some of you, it is precisely, of course, the language of mass action kinetics. Now, you could ask me, is mass action kinetics relevant to this? Should I be using stochastic simulations? Those are all great questions. Now, one of the things that you quickly realize when you approach any piece of biochemistry like this, and this is actually one of the hardest problems we have, is the word models, that's what we call figure 7 there, the word model, or the little pictograms that you get out of reactions, are in fact extraordinarily simple. And so, for the piece of biology that I showed you that structure before, so here's VID coming along, activating the 4-containing protein, which is supposed to auto-activate and multimerize, locally antagonized by BCL-XL. And this is essentially the picture that you would pull out of reaction. But you or I, if we actually were to read the papers in great detail, we realized that it was much more elaborate and uncertain than that. And so I'm still showing you a picture rather than the mathematics. What we now realize from David Andrews and work in this field is that there are both processes of translocation that are absolutely essential. There are binding reactions and there are catalytic processes here. And there are processes, and I've dotted one here in the blue case, which is BCL-XL recruiting its own cytosolic species of mitochondria that has not been documented in any public papers, but make a lot of structural sense. So you might want to put that forward as a hypothesis test. So ultimately, you have to arrive at some prior understanding of that. And what we have found is that really there is no graphical annotation that can adequately encapsulate the hypothesis you want to set. And in the end, that's why you end up with a series of mathematical equations. And the models I'm showing you today use about 100 variables, about 100 equations. And this is a little bit of that line. And the neat thing about this, of course, it's no more than I showed you before. Its very enumeration makes it seem complex. The idea is fundamentally simple. Mass action mechanism. And in the end of the day, the nice thing is you can now begin to do simulation models. And you can ask, well, did it matter in principle whether BCL-XL could auto-recruit the membrane?
And by investigating it, has opened an entirely new avenue of investigation and research. It's hard to imagine a better example of that very phenomenon than today's speaker, Dr. Daniel Kastner. Dan is the chief of the genetics and genomics branch of NIAMS. He's the clinical director and director of translational research for the intramural program of NIAMS. And for the last year, he's also served as deputy director for Intramural Clinical Research at NIH. I've known Dan for more than 10 years, had the privilege of a little bit of collaboration with him back in the 1990s in the search for one of the genes that I'm sure he's going to talk about today, which is responsible when mutated for a condition called familial Mediterranean fever. Dan has really established that whole area of periodic fevers, and a new kind of term that he invented for that, namely the auto-inflammatory condition that includes FMF and a number of other related disorders that have opened our eyes to a whole area of the immune system. Certainly, as many have pointed out, you never understand a system as well as when you have the opportunity to observe what happens when something goes wrong in one of the components of these genetic conditions, although rare, have certainly provided that kind of remarkable insight. Dan got his undergraduate degree at Princeton, his MD PhD at Baylor, and he stayed on at Baylor to be resident and ultimately chief resident in internal medicine. But since 1985, he has been here at NIH in various roles, and I mentioned to you the one that he now holds, actually several that he now holds, playing a very important leadership role in clinical research here at NIH. He's been elected to membership in the American Society of Clinical Investigation and the Association of American Physicians. Has been honored particularly by the ACR Distinguished Investigator Award from the American College of Rheumatology, and currently is an NIH Distinguished Investigator, one of those terms, those appointments reserved for our most highly respected and credentialed investigators here at NIH. So it's a great pleasure for me to have the chance to introduce him, and I'd ask you to give a warm welcome to my friend Dan Kastner.
Thank you very much, Francis. Well, thank you very much, Francis, for that very kind introduction. This is going to be a real adventure in many different ways. In point of fact, this particular talk was the first time that I had embedded a video in one of my PowerPoint presentations. And we've been sort of fiddling around with the audio-visual system over the course of the last hour, trying to get it to work. So we'll see what happens. If we don't get the video, I may have to recount to you what in fact happened during that interview a couple of days ago. But in any case, the title of the talk today is going to be Fevers, Genes, and Histories, Adventures in the Genomics of Inflammation. And basically what we're going to be talking about today are these diseases, such as familial Mediterranean fever that Francis alluded to, that have had really a special fascination for me for the last over 20 years now, and that have really been the subject of our work in the laboratory, looking for the genes that are mutated in these Mendelian disorders. And my feeble attempt at a pun here is history, so we're going to be dealing both with the histories of patients that have sort of gotten me interested in these diseases, and then looking perhaps a little bit at insights that we get into histories of human populations that we learn through some of the analyses of the genetic information associated with mutations in these genes. So it really has been, over the course of the last few years, an adventure for me, and hopefully we will enjoy the next little while as we take adventures through time and space, both real and imagined, as we talk about some of these diseases. Now, perhaps if I push this button, it will advance, but I can see it won't. But the person in the back got the cue, and so we are now onto the second slide, which is the hereditary periodic fever syndromes. What are they, and why should you care? So, first of all, if we can have the first bullet here, these are disorders that are characterized by recurring episodes of fever with either localized and or systemic